Pluto, a distant and bewildering, more modest planet, was once a singular individual from our nearby planetary system's planetary family. However, later disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a shocking revelation. They suggest that this chilly world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a unique astronomical phenomenon? Or is there something else to this impending cosmic disaster? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, once considered a planet but downgraded to a dwarf planet due to its erratic orbit, remains a subject of interest and study in the scientific community. According to recent predictions by leading scientists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising alarms about a potentially catastrophic collision between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unlike any other planet in our solar system. It requires a staggering 248 years to complete one orbit, meaning that since its discovery in 1930, it hasn't even finished a full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its exceptionally elongated shape, completely deviating from the near-circular orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much more extreme compared to the other planets, and this inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its conjunction with Neptune's for about 20 years in each orbit. During this time, Pluto actually moves closer to the Sun than Neptune, contrary to what one might expect based on their positions in the planetary system. This raises the common question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to understand its unique path compared to other planets, whose orbits are more closely aligned with the ecliptic plane. Pluto's orbit stood out due to its steep inclination and irregular shape. The mystery deepened with the realization that Pluto's orbit does, in fact, cross Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space concerns the interaction between three objects, such as Pluto, Neptune, and the Sun, and how their gravity affects their movement. It's akin to trying to predict where they will go based on their starting positions and how they influence each other. In Pluto's case, this issue demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all collaborate in a complex manner. Terms like asymptotic libration, scope libration, and VSK oscillation are part of this puzzle. According to astrophysicists, what keeps these planets in their orbits is a form of libration, particularly with respect to Pluto and Neptune. Libration, in this context, means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Scope libration, on the other hand, refers to the upward movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding an extra layer of protection against potential impacts. Another vital factor in this scenario is the VSK oscillation, named after researchers V.A. Vopel, A.S. Mikhailov, and L.V. Kolodov, who studied the movement of objects in space. This phenomenon concerns how three space objects, like Pluto, Neptune, and the Sun, influence each other's motion through gravity. This gravitational interaction helps maintain Pluto's orbit stable for an unexpectedly long time. Despite the apparent chaos in space, VSK oscillation reveals that certain patterns and forces preserve order in the universe. These mechanisms, along with the gravitational influence of other planets, help keep Pluto's orbit stable, preventing it from crashing into Neptune or drifting off course. The three-body problem aids in understanding how the orbits of space objects can change due to their gravitational interactions. By studying this, we learn more about Pluto, our planetary system, and distant stars and planets. Numerical simulations in the late 1980s uncovered that despite these stabilizing mechanisms, Pluto's orbit is actually chaotic. Minor deviations in its starting conditions could lead to significant changes over long periods of time. However, these surprising properties of Pluto's orbit have been found to maintain stability over incredibly long timescales. Later computer tests showed how the gravitational pull from giant planets like Neptune, Jupiter, and Saturn influences Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance helps stabilize Pluto's orbit. However, Neptune is not the only planet assisting in this process. Jupiter's gravity also plays a crucial role in safeguarding Pluto's orbit, with Saturn also contributing. These tests suggest that Jupiter's gravity alone is powerful enough to ensure Pluto remains on a steady path for an extraordinarily long time, potentially even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues moving safely in space without running into trouble. These factors are significant in the broader context of the universe because they contribute to the stability of celestial bodies' movements. Without such forces, the nearby planetary system would be far more chaotic. Bodies like Pluto might crash into others or be ejected from their stable orbits, triggering a cascading effect on other celestial bodies. For Pluto, especially with discussions about a potential collision with Neptune in the future, understanding its orbit is essential. This provides us with a clearer picture of the dynamic nature of our planetary system. The case of Pluto illustrates how even the most seemingly unstable orbits can reach a state of equilibrium through the complex interaction of gravitational forces and orbital mechanics. It also emphasizes the importance of steady observation and research to better understand our position in the universe. Exploring the depths of space often forces us to confront the erratic nature of celestial bodies, and Pluto's orbit is an ideal example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in the case of Pluto. This means that even small variations in Pluto's position or speed can drastically change its long-term orbit. Virtual simulations have been invaluable in helping scientists figure out how Pluto moves through space. These simulations use complex mathematics to replicate the gravitational interactions between Pluto and other space objects like Neptune. By adjusting small details in the simulations, astronomers can observe how even the tiniest changes can result in a vastly different outcome. In the late 1980s, these simulations revealed an interesting finding about Pluto's orbit. Despite having mechanisms like asymptotic and scope libration to keep it stable, its orbit can still be erratic. If you start with even a slight difference in Pluto's position or speed, its path can appear dramatically different over many years. Nevertheless, despite this apparent chaos, Pluto's orbit remains stable for billions of years. This means that Pluto's journey around the Sun has an underlying order, even though it might seem erratic at first. Predicting major events, particularly those involving turbulent orbits like Pluto's, presents enormous challenges. The inherent unpredictability of these systems means that long-term predictions are filled with uncertainties. While numerical simulations offer valuable insights into the future behavior of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to radically different results, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits, like Pluto's, reminds us of the ever-evolving and dynamic nature of the universe. While we've made significant progress in understanding space, Pluto's case serves as a reminder that our knowledge of the universe is still limited. Understanding the gravitational effects of giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the solar system. It illustrates how the position and presence of each planet can have far-reaching effects, influencing the stability and direction of other bodies within the system. So, why are prominent astrophysicists only now raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces working to prevent it? Neil deGrasse Tyson, a renowned astrophysicist, offers a fresh perspective on the mysteries of our nearby planetary system, especially the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto as a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the forgotten corners of space. Tyson views the reclassification of Pluto not as a demotion, but as a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of continuous learning and transformation. He recognizes the complexities of Pluto's orbit, as well as its interactions with Neptune, through a lens that acknowledges the eccentricities of space. Tyson suggests that while Pluto's orbit is stable now, it could undergo significant changes in the future. This possibility serves as a reminder of how much we still have to learn about the forces shaping our nearby planetary system. In conclusion, Pluto's orbit is a captivating example of the complex interplay of gravitational forces within our solar system. While its path remains stable for now, the intricate dynamics between Pluto, Neptune, and the other planets suggest that even the most seemingly steady orbits can change over time. As astrophysicists like Neil deGrasse Tyson continue to investigate the mysteries of the universe, they help us better understand the delicate balance that governs the movement of celestial bodies. The potential for a Pluto-Neptune collision isn't necessarily inevitable, but it is a testament to the constantly evolving and unpredictable nature of the universe. Notwithstanding the scientific theories surrounding Pluto's orbit, it is important to consider the broader implications of these dynamics for our understanding of the solar system and the universe at large. While Pluto's journey remains a subject of intrigue, it also serves as a reminder that the universe is full of hidden complexities awaiting exploration. The concept of orbital resonance, particularly between Pluto and Neptune, is a crucial piece of this puzzle. This resonance, where the ratio of Pluto and Neptune's orbits is 2:3, is a remarkable feature of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This ratio ensures that despite their orbits crossing, the 2 planets never collide. This phenomenon is a result of gravitational interactions that stabilize their paths and work together to prevent any catastrophic impact. Pluto's orbital dynamics continue to fascinate scientists, as the intricate forces at play have created a stable yet eccentric path for this dwarf planet. The gravitational interactions between Pluto, Neptune, and the other planets are not only essential in preventing a collision, but they also reveal the deeper complexity of our solar system's architecture. Pluto's orbit, while highly irregular, remains consistent due to these forces acting in unison. This balance, maintained over billions of years, shows how cosmic forces can stabilize even the most unusual and unpredictable of orbits. An important aspect of these cosmic interactions is the role of orbital resonance between Pluto and Neptune. This resonance is not just a numerical coincidence, but a crucial factor in ensuring that these 2 planets do not crash into each other despite crossing paths in their respective orbits. The 2:3 orbital resonance ensures that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance is precisely timed so that when Pluto and Neptune appear to cross paths in their orbits, they are always positioned at safe distances from each other, with no risk of collision. This delicate mechanism is a testament to the profound precision with which the gravitational forces operate within our solar system. While the mechanisms that stabilize Pluto's orbit are well understood, the long-term behavior of Pluto remains a topic of active research. There is always the possibility that changes in the gravitational influence of other planets, or even the Sun's activity, could alter Pluto's orbital path over extended periods of time. Although Pluto's current orbit is stable, minor shifts in its position or velocity could have significant effects on its trajectory. This is where the concept of chaos theory comes into play. Small variations in initial conditions can lead to vastly different outcomes in the future. Moreover, the study of Pluto's orbit is helping astronomers refine their models of other celestial bodies and systems. Understanding the factors that govern Pluto's movement and its relationship with Neptune can provide valuable insights into the behavior of other distant objects in our solar system, as well as those in other star systems. For example, scientists have used similar principles of orbital dynamics to study the movement of distant exoplanets, enhancing our understanding of how planets and their moons interact in different environments. The potential for a change in Pluto's orbit is also a reminder that the universe is far from static. Celestial bodies are in constant motion, subject to influences both known and unknown. While the forces that govern Pluto's current stability are well documented, there is always a possibility that new discoveries will reveal previously unseen forces at play. Understanding Pluto's orbital mechanics is crucial not only for the study of this specific planet, but for the broader study of the solar system and the universe beyond. Astronomers continue to gather more data through space missions and ground-based observations, offering an ever-clearer picture of Pluto's movements. For example, NASA's New Horizons mission, which flew by Pluto in 2015, provided unprecedented close-up images and measurements of the dwarf planet, contributing to our understanding of its surface, atmosphere, and even its orbital dynamics. This data is invaluable, allowing scientists to refine their models and test theories about Pluto's future movements and potential interactions with Neptune. Despite the stability of Pluto's orbit, the future remains unpredictable. As new data is collected and simulations become more sophisticated, scientists can continue to refine their understanding of this distant world. But the unpredictability of Pluto's future trajectory is a reminder of the complexity and mystery of the universe, where even the most stable systems can change over time. In this way, Pluto's orbit serves as both a case study and a symbol of the many mysteries still waiting to be uncovered in the vast expanse of space.